All right, so for those of you that don't know who Newton is, Sir Isaac Newton is considered by many to be one of the most influential people in human history. And in his book, he describes the laws of motion, those being the 3 laws that we're going to consider today. Also, Galileo Galilei in the early 17th century made an observation. A body at rest remains at rest, and a body in motion continues to move at a constant velocity in a straight line, unless acted upon by an external force. So if there's no friction, there's no air resistance, there's absolutely nothing. So for instance, you're in space, there's no forces acting on you, and you are traveling at a constant velocity, you will be traveling at that velocity infinitely in time as long as no external forces are acting on you. That is in the form of gravitational forces by planets or some resistance, air resistance, not that there is any air in space, but if you do encounter something or something hits you, an asteroid, that's an external force. So if none of those are present, it's just you in space moving at a constant velocity, you will be moving at that constant velocity forever. Does put a smile on your face, doesn't it? All right, so he also discovered that if an object is traveling at a certain velocity, there's no force necessary to keep it traveling, like when you're in space. Newton's first law sort of shows that as well. Every body perseveres in its state of rest or in uniform motion in a straight line, unless it is compelled to change that state by forces impressed on it if you got hit by an asteroid. Or if you're moving past the planet and that gravitational force is pulling you towards it, that is external forces. Or if somebody pushes you in space, that's also another one. It's important to know that you should not be accelerating. If you're accelerating at a constant acceleration, then this law does not apply to you. You need no acceleration, just constant velocity. All right, so that was the first law. Now we go on to the second law. There's a little picture of a spring that's connected to a mass, and you can see x1 is its position of rest. So there it's standing still, nothing's happening, and then I go and I pull it away from the wall to a distance x2. So now I'm stretching the spring, and it produces a pull force back in the opposite direction of where I'm pulling it towards. All right, and mass 1 has got an acceleration of a1, which is essentially 0 because that's the position of rest. And when I pull it to position x2, it now has an acceleration a2. Right, so those are the two conditions. There's a condition at point 1 and there's a condition at point 2. And that can be written as that equation. You can see the A has been bold written, meaning it's a vector. It's got a magnitude and direction. Okay, so putting that in words, a force acting on a body gives it an acceleration which is in the direction of the force and has a magnitude given by ma. So when I push someone, that someone suddenly accelerates in the direction where I'm pushing him. All right, so if somebody's standing in front of me in a queue and I do not like him and I push him forward, he will accelerate forward in the direction I'm pushing him with the force which is being forward as well. All right. If somebody is standing behind me and I push him backwards, then he's accelerating backwards, which is the direction of the force I'm exerting on him. Everybody get our idea? All right, so accelerating in the same direction as the force being applied on that object. That is essentially Newton's second law. So you can write that mathematically as F equals ma, and this unit is in kilograms meters per second squared, which is essentially Newton. All right, so what about gravity? So when dealing with gravitational forces of an object, the acceleration in Newton's second law is the gravitational acceleration, which is g, and we take g as 9.81 meters per second squared. It's a vector, it's typed in bold. What is the direction of the gravitational force? Can anybody tell me? Center of the Earth, yes, downwards. Oh, actually downwards, there it stands, okay. All right, so, directed downwards, and Fg is known as the object's weight. So you get mass, your mass is a certain value, and then you've got a different value for your weight, which has got a direction, and that is always downwards. We're going to the third law. So we've covered first and second law. Third law states that if one object exerts a force on another, then the second object exerts the same force in the opposite direction to the first object. So if I push you, you push back. If I push down onto the table is pushing back up. So every action has got a negative reaction. Minus sign indicates that it's in the opposite direction. All right, so when somebody tells you every action's got a reaction, tell them they're wrong. So every action got a negative reaction. Right, so example that we can go through. So there we have two masses, mass 1 and mass 2. You can see they're different sizes, meaning they've got different weights. And there's a force that is being exerted from the left to the right onto these masses. Giving the values, mass 1 is 5 kilograms, mass 2 is 15 kilograms, and the force is 20 newtons. So Newton's second law states in scalar form that F equals ma. So m being mass 1 plus mass 2 because they're actually touching, so you can see them as one unit. 5 plus 15 kilograms times the acceleration. Acceleration we don't know, we know the force, so we can rearrange that equation and we can get the acceleration as 1 meters per second squared. So that is the acceleration of that collection of masses, so mass 1 and mass 2. Now we can take it further and we can just look at mass 2. So obviously mass 1 is the primary recipient of the force. So force that F pushes mass 1, and mass 1 accelerates, and as a result pushes mass 2. And then you can see, you can redraw that free body diagram as the force 1, 2 is being exerted at mass 2, which is essentially mass 1 is pushing mass 2. So then we can quickly calculate what that formula of that force is. So for mass 2 is experiencing a force of 50 newtons as a result of mass 1. So mass 1 is feeling a force of 20 newtons, is accelerating into the direction of that force. It encounters mass 2, pushes mass 2 into the direction that it's moving as well, and with 50 newtons to the right. And then similarly, we can look at the force that mass 2 is pushing back with. So because mass 1 is pushing mass 2, mass 2 is pushing back. And then you can update the free body diagram as the force, which is 20 newtons, going to the right. There's a reactive force in the opposite direction, mass of force 2, 1. And we want to know now what is that force. And that is exactly the same as force 1, 2. It's just in the opposite direction. That's again saying Newton's third law. Every action has got a negative reaction. Okay, so we can get particles and rigid bodies. In mechanics, real bodies are modeled using certain idealizations. So we sort of simplify all these bodies. If it's a person, if it's a car, if it's a building, you can simplify it to an extent. So you can simplify it to just a particle, that being just a little dot on the paper. It has a mass, but no size or shape. And particles cannot have couple moments applied to them. So it's literally just linear forces. And we use the rectangular coordinate system with particles. So that's the X, Y, and Z coordinate system. And then you can use rigid bodies. This is a bit more complicated because then you add the size and shape of the part as well. So if it's a person, you're actually considering the person. If it's a car, you're looking at the person, the car as a whole. And you can now act, couple moments can be applied to it. So here, center of gravity comes into play. If you're not pushing or pulling directly from the center of gravity, then mass center, then there is a moment that's being generated as a result. So going ahead, we're just going to look at the particle. And when a system of forces acts on a particle, then Newton's second law may be written in the form that the sum of all forces equals ma. So that there's not always just one force acting on a system. There can be multiple sources. So if you push something, your force won't be the only one. There'll be gravitational forces, there'll be frictional forces, etc., and a bunch of other additional ones. So the sum of all that external forces equals its mass times acceleration. All right, so one way that makes your life, again, really easy is to, when you encounter a problem for Newton's laws, to first draw a free body diagram. It helps you visualize the forces, it helps you determine what direction they are, just to make your life easier when you are using the sum of F equals ma equation. All right, so definition of free body diagram is a sketch of an object free of its surroundings and then showing the external forces that acts on it. That's usually done by arrows, showing you the direction of these forces and angles if there are any. All right, and then we get a kinetic diagram. That is essentially just showing you in what direction it's moving. So if it's moving to the right, you get an arrow showing you it's going to the right. If it's moving upwards, arrow upward, downwards, down. So that's essentially what it is. All right, and these two are equal to each other, which in a sense is F equals ma. F is all the forces. The free body diagram has got all the forces on it, which is the sum of all forces, equals the kinetic diagram, which essentially just shows you which direction it's going. So that is just like a visual representation of the equation F equals ma. All right, so following steps you can follow to draw a free body diagram is to select a coordinate system. We just reducing it to one particle, always choose a rectangular coordinate system. This will become more important in the next chapter when we're actually going to do all the calculations of it. And then you need to go and identify the object you wish to analyze and just draw it as a block. So it's like a block of no size or shape. It's just making your life easier in representing the forces. It's literally, it can also be a particle, but it's difficult to describe all the forces if you've got just a little dot on the paper. So the rectangular makes it a bit more easier to visualize. All right, so then we draw all external forces acting on the particle and label them. Directions of forces having unknown magnitudes can be assumed. So if I want you to calculate an external force, but I don't give you any information about it, you can assume a direction. You can say, I assume this is in the positive direction, so it's got a positive sign. Or you assume it's in the negative direction, it's got a negative sign. If you assume it incorrectly, your answer will correct you. So if you're assuming it's in the negative direction or in the positive direction and you get an answer that's in the negative direction, that means you've assumed it incorrectly. So you don't need to worry about if you're going to assume incorrectly. Your answer will tell you if you're correct or not. All right, so the direction of acceleration of the body's mass center A should be established and identified on the kinetic diagram. So again, that is just the other one. You need to decide what direction is positive movement, what direction is negative movement. So that will then influence the direction of all the other forces. You need to specify that on the free body diagram as well. All right, so we're going to go and have a quick example of the Bloodhound for those of you that's not familiar with the Bloodhound car. So if you consider this as a free body diagram, you get the thrust force, which is generated by its engines. What other forces is acting on it, which is not shown here? Drag, all right, yeah. Air resistance. Weight, yes. Gravitational resistance. Frictional resistances. So usually you can be, if there's just one external force, like in this case the thrust force, the ones that are standard are usually your gravitational forces and your frictional forces that's always there, your normal forces, and then any additional forces that's been given to you. Yeah, need to determine the coordinate system. It's one-dimensional. It's not a flying car, so we're just going to consider the x-axis. We need to identify the object of analysis. In this case, it's the car itself, drawn as a block, so you can just draw it as a block. And then you need to draw all the external forces, which we've just listed. Yeah, so that you can reduce that to that block and add all the additional ones. Frictional, gravitational forces, and air resistance is another one, yeah. And this is how you go and draw the kinetic diagram. You can see it's literally just a block showing you the direction of movement. Kinetic diagram accelerated will occur in a positive x direction. You can see we showed above the free body diagram, you can see there's an arrow with the x. That is showing that that direction from right to left is the positive x coordinate system. So then all your forces that's going to show to the left will be positive forces. In some cases that can flip around, and then if the x coordinate system is going from left to right, and that's being taken as positive, and then all the forces needs to be updated accordingly. So it's always important to make sure at the start you need to determine which direction is positive. If there's a y-axis, you need to determine is up positive or is down positive. All right, so now when we consider friction, so block is sitting on a horizontal surface and is gradually increasing, pushing force is being applied. So for small forces, when the P force is really small, you could literally say the force F subscript F, which is the frictional force, equals the force pushing on it. So that means they're the same. It's not moving the block then, because the magnitude of the force pushing the block and the magnitude pushing back is the same. And then for larger forces, when the block is actually moving, you can get the frictional forces is a coefficient of friction times n. And then that is for the frictional forces when you go and when the block is moving. You can get a simple model and an advanced model. The frictional force will be equal to the applied force until the applied force is is more than the frictional force. Then the block will start moving. And you can see there's a nice little transition. It's just going straight and then flat. With the advanced model, you get a static coefficient of friction and you get a kinetic coefficient of friction, meaning that the coefficient of friction is different for a block that is standing still versus a block that's moving. And you can see that when the block is moving, the frictional forces are less than when it is standing still. So that is a bit more of an advanced way of doing it, in a sense. So this is a crate that is being pulled by an external force P, 400 newtons, at an angle of 30 degrees north from east. And now I want you to go and draw a three-body diagram showing all the forces that's acting on it. And you can see the coefficient of friction is given as just mu, so there's no static or kinetic force coefficients given, it's just the one, so we're using the simplified model. All right, so I'm going to give you some time to draw that. Get a pen out and a paper and see if you can master the art of drawing a free body diagram. All right, so first thing first, you need to determine the coordinate system that you're going to use. In this case, we've got a force that is being applied at an angle. So we are going to have a component in the x direction and a component in the y direction. So we need to determine what directions of the x and the y components are positive. So you can just start off by drawing at and saying this is the positive x and that is the positive y. So you've determined that. That is the positive and negative forces. And now you can go and just draw the block. And the first thing is that the force that's been given was P as 400 Newton in the positive x direction. And then you get the gravitational acceleration downward and the reaction force as a result of that downward. And then you also get a frictional force. That is the free body diagram, but do not forget the kinetic diagram.